About thiols again. I'm going to start talking about the sulfur analogues of alcohols. And I mentioned a little bit of this last time, the idea that the OH group is replaced by the SH group, and the chemistry changes somewhat because the thiols are more acidic. Their odors definitely change. Thiols are notoriously smelly, and you can definitely tell when people are using them. Nomenclature is fairly straightforward. I'm not going to spend an awful lot of time on that. What we really need to worry about here is chemistry. So the pK of a SH bond is enhanced because the S is bigger and the anion is therefore more stable. And if you want to introduce an SH bond, all you simply do is an SN2 reaction in which you take a halide, introduce that nucleophile, and there you go, that's it. And you know it's SN2 in this case because it's a primary system. You can prove this by doing chemistry on chiral materials. You can start here with a particularly starter material of one configuration and then attack it with this sulfur nucleophile and end up with the inverted product. That tells you it's an SN2 reaction. And so you'll see this in multi-step synthesis. You'll see this in the textbook. You might see it next week. Start out with a halide, do a substitution like that, and then use the thiol for something else. We'll see that in a second. The chemistry here, nothing too tricky in terms of anything new, just acid-base chemistry. The pK of a thiol is typically about 10. And so if you treat it with a base, something strong like hydroxide, you'll get pretty much complete deprotonation, and that will give you what's called here a thiolate anion. And that thing then is powerfully nucleophilic itself. So we do the acid-base chemistry again to set up a nucleophile and to do something else. We've got some interesting chemistry here that's more applicable to biochem later. We can do this in the lab, but it's typically more of a biochemical process that you'll see with what we call disulfide linkages. Over here, disulfide linkages help to give proteins some three-dimensional structure by linking together within a protein. In the lab, you can make them by doing this. You simply take S- and you treat it with something like bromine. It's a little bit different, this. All right, so S- is it's bigger, it's more polarizable, it has some interesting properties. It can attack and it can be attacked. A little bit different. So in this case, what we do in that first reaction is an SN2, and then in the second reaction, we might bring a second equivalent of that nucleophile in and do a second SN2, kicking out the bromine. All right? That type of compound doesn't have a lot of use in organic chemistry, but later on with biochem, you will have to understand how that sort of process works. More interesting when we see the use of alkyl groups, we'll be able to alkylate these things, but there's the overall chemistry. Two equivalents of a thiol, treat it with a base in the presence of bromine, and you can produce a disulfide. To get rid of the disulfide, you can think about how to do that. This is an oxidation reduction type process. If you want to give this a couple of hydrogens back, I would suggest you have to break that bond, and that involves a reduction. And you can remember from the past, if we use zinc, something like zinc and HCl, you can reduce things down. No mechanism for that one, obviously, right? That's very similar to stuff we've seen before, and we didn't worry about a mechanism. Napoleon Pierce. No, the zinc is to actually introduce electrons into the sulfur, and then we lose the hydrogens. It's actually a very complicated mechanism that we don't cover. All right. Now, in terms of other compounds that are related to sulfur, to thiols, things like sulfides. These are the equivalent of ethers. You've seen ethers as the oxygen equivalent, and now we have sulfides as the sulfur equivalent. Where have we seen this before? If I put two methyl groups on here, where did we see that before? Ozonolysis, right? Reduction of the end product of an ozonolysis, DNS. I'll show that again in a second. Nomenclature is fairly straightforward. This is diethyl ether with the oxygen attached. The sulfide tells you there are two carbon groups attached. All right, so thiol says one carbon group maybe, and then sulfide says two carbon groups. And these things have lots of use, not so much as solvents, but certainly as reagents. How do you make them? Quite straightforward. This is just repetitive because this is basically the Williamson ether synthesis. What you would do in the first step is treat this with a base, take the proton off, and then you make this negative, and that does an SN2, and that gives you a sulfide. So it's pretty straightforward. There's nothing too tricky about that. There's the chemistry. Mechanistically, again, we don't have to worry about it so much because it is, if you see it, it's straightforward. There's nothing really new there. But that's a very, very powerful way of making sulfides and also making unsymmetrical sulfides, right? You can use whatever you want for the R groups and introduce that quite easily. In terms of other possibilities, this is more FYI. This is a useful reagent that you can make in the organic lab. And this is more of a graduate level type of reagent, but this is how nucleophilic sulfur is. We didn't see oxygen in ethers alkylated. We did not use an oxygen in an ether as a nucleophile. We used it as a base, and we could protonate it with a powerful base, but we did not use it as a nucleophile. Here, you can use the sulfide as a nucleophile. It's that nucleophilic, it's that powerful. So what's happening here is in the presence of some alkyl halide, like an iodide or a bromide, you're getting a substitution reaction. And this produces this sulfoxonium type salt or sulfonium type salt. Not so much interested as an organic chemist at this point because it's more of a graduate level stuff, but when you get to biochemistry, you will see this as a very useful alkylating reagent. We've got this structure here, S-adenosylmethionine. I'm going to just tell you about this right now, and then we'll talk about it maybe in the last couple of weeks of class. There's that substructure. There's sulfur with 3 valences, 1 methyl group and 2 other carbon groups. That's the same type of structure as the one on the previous slide, a sulfonium salt. Now, all of this stuff for the biologists, all of this stuff, okay, isn't that interesting, okay? We'll just call it R. I'm sorry. Tell Dr. Cooper I just did that, yeah? Back at him. What I've got here is a big leaving group, because what will happen is a nucleophile will come in the biological sense, it will attack that methyl group and boot this out. And that fits in very nicely with our sort of paradigm of making a leaving group a good leaving group. Make it positive, because if it breaks back off, it becomes neutral, and nothing better than that. So you'll see a lot of that later. Right now, there's how you make them in the organic lab, and they're quite versatile. You can actually alkylate them and then dealkylate them, and you can shuttle alkyl groups around. Most of you who are interested in biochem will get to know this molecule at great length. All right, I'm trying to get out of this because it's pretty dry. There's not much to it. I want to get into the next chapter, which is great. All kinds of fun. You can oxidize these things. Sulfide, we actually saw the sulfoxide here as the product of an oxidation when we did the ozonolysis process. We took DMS and we took out oxygen and we ended up with DMSO. And you can go further. Because sulfur is further down the periodic table, it's actually more flexible. You can think about phosphorus being +3 or +5. Sulfur can be +2 or +4 or +6. It can expand its octet because it's more flexible and it's bigger. Sulfones we don't deal with a lot in this class. We would at the senior level stuff, 5821, or in the graduate class. They're very versatile reagents. And this is very similar to sulfuric acid. If you were to put the hydroxyls there instead of the R groups, you're familiar with that. You're familiar with sulfuric acid. And if you put carbon groups on here, all of a sudden we have a very powerful, versatile set of reagents for an organic chemist to use later on. You can see here how to do this. You need some oxidant. There's a powerful oxidant, sodium iodide. There's a powerful oxidant, peroxide. And you can turn these things into sulfoxides and sulfones. I'm not going to worry about that in terms of exams, but you've seen it, it's there. So sulfur is very versatile and very useful as far as I'm concerned as an organic chemist, and you will see very, very useful in biochemistry later on. In terms of some of these uses, we've seen this I think before, these things can be quite polar. You think about DMSO, where these 2 groups are methyl groups, that led to a very good, potent polar aprotic solvent. It was very good at SN2 reactions because it dissolves things up and it does not participate. And it's all based on this dipole, based on different electronegativities. And likewise with the sulfones, they've got some properties based on being a powerful electron withdrawing group that you might see later on. This is where you've seen these things, use of ozone to break apart a alkene into 2 carbonyls, and the side reaction that we talked about, and we did draw a mechanism for this, that's ripping out an oxygen to become DMSO. So it's just going back and showing you that this stuff is important, and because they're related to alcohols, that's why it fits in this particular chapter. Michael? I don't know. I don't know. I'm going to guess this isn't quite as reactive as peroxide. Yeah, but it's, it'd be an interesting experiment to try, see if it did it. And then argue about bond strengths and that, and which one's more reactive, which one's less reactive. But in this reality, it stops at DMSO. Okay. Now, to finish this off, this is very similar to what we did in recitation, for those of you who are in recitation, which is most of you. Those of you who aren't, you're kind of flying solo, and good luck next week, because a lot of this stuff is built up from knowing the basic reactions and then being able to put it into practice and doing chemistry, doing synthesis. We've been practicing synthesis problems in recitation, and we will do again this next week, getting ready for this exam. You can pass the test, not having recitation, that shouldn't be a problem, but you'll be better prepared if you're in there practicing these problems. Now, we started out with epoxides in this chapter, and epoxides became very useful because they're spring-loaded electrophiles. They're very good at being attacked and opening up. And if we don't have any protons around, the nucleophile goes for the less crowded carbon, right, in an SN2-like process. And if we put protons in and we make this a O+ leaving group, then if you have a tertiary system, it goes like an SN1 type reaction. So there's a lot to do with that. And we know that epoxides are easy to make, and we know that the sort of inherent sort of strain in that system is going to help it break open. And all of a sudden, they become very potent electrophiles. And we can bring in nucleophiles of different types, and we can attack these carbons because they're at least delta plus, and that gives us an expanded, more complicated product. But I'll say this again. look where the nucleophile is relative to the functional group. It's on the next carbon along. If you did this with a Grignard, for example, and you did it with a carbonyl, the new group that you introduced ends up on the same carbon as the oxygen. Now you've got some flexibility because with epoxides, you can put the nucleophile on the adjacent carbon, and that will make some difference when you're trying to solve problems. So what we'll do to finish up this chapter is just the synthesis stuff, the synthesis strategies that's always at the end of these chapters now, and try to think about applications and then move into the spectroscopy material. So let's say next week you're given some problem. There's the product, there's the organic material that you were given to actually solve the problem. What type of chemistry do we have to do? It's obvious that we have to oxidize something. We're bringing in oxygen, okay, and we have to get rid of some hydrogen, so that's an oxidation. So we have to worry about what we'll do. And we do have some chemistry that will allow us to oxidize on both carbons. And by oxidize, I can think of ozonolysis, I can think of introduction of O with MCPBA, stuff like that. Those are all oxidation reactions. And your job, as you practice these things over the weekend and think about next week, is to worry about things like stereochemistry, worry about regiochemistry, and then be able to put it into practice. So in this example, I'm starting with an alkane, and alkanes don't do very much. And if you kept on top of this stuff, what's about the only useful synthesis that we do with alkanes? Substitution with a halogen, right? So you might think, all right, I need to put a bromine on there. And since you have two carbons involved, both these carbons are involved, what's the simplest functional group you can think of that has both carbons involved? An alkene. Carbon-carbon double bond. It's as simple as that. So if you can get to the alkene, you can probably get to this product. And the trans outcome here, this is more sophisticated, but it's, again, this is where we're at. The trans relationship between those two materials there, that suggests that it isn't a cis dihydroxylation, right? It's not a syn dihydroxylation with osmium. It's more like an anti-trans system in which you're making epoxide and then you open it up somehow. So thinking about how to put these things together, chances are there might be more than one way to do it. One way might be better than the other in reality, but on paper we're happy that things usually work. So what you would do here is recognize what I just said. Two carbons need to be involved. That probably involves an alkene, so at some point make an alkene. In the first step, put the bromine on, and then we would go to here. And the question would be, what type of reagent? If I use T-butoxide, is that appropriate for that type of step? I'm trying to do an E2 to make an alkene, but why would that not be the best choice? That would typically, it's big, and it would typically go for a less crowded proton, and it might give you the Hofmann outcome. So what you'll choose instead is maybe something like sodium methoxide or sodium ethoxide. And that will give you a clean E2 in which the Zaitsev product is favored, which happens to be this one right there. So that's no good. After that, hopefully things are starting to click, and you can see, right, I need to put in an epoxide because I need to worry about adding something from underneath. And in this case, would this be 1 enantiomer, or would it be plus minus? Plus minus, right, because it's a prochiral starter material, and you'll get the racemic mixture. Now, to get this thing finished, what would happen if I chose something like sodium methoxide? If I chose this as the reagent, because it's obvious I need to bring in OMe, is that going to give me what I'm looking for? It is not. Any ideas why? It will go for the less substituted carbon. It will go for there, which is the wrong way around. So you've really got to be on top of stuff here, because you have the possibility of a tertiary system which can give you a tertiary carbocation-like intermediate type structure. The acid catalyzed reaction will give reaction at the tertiary carbon instead of the primary carbon. So again, you know, how deep is this stuff? How important is this stuff in terms of depth? You really have to be on top to be able to get the whole thing finished. Pierce. In that final step where you want to no, because water is not acidic enough to make that reaction go. It's not acidic enough to protonate the O to make it a good leaving group. You'd have to use an acid. It would be sulfuric acid, something like that, catalytic, because you would get it back in the reaction. Even with methanol. Why are you curious about why not methanol? Okay, but the base here, I mean, this is just as basic as methanol, isn't it? sp3 hybrid oxygen is about the same basicity, you would think. And so even if the methanol takes a proton, some of the protons will be on the oxygen. It'll allow the process to happen. Okay, so with these types of things, practice, 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 and then when you're done practicing, practice again. What exams are next week? Any biology exams next week? That's all pretty straightforward stuff. You don't need to worry about that. Worry about the chemistry. Now, the starter material here happens to be an epoxide again. We know how to make them, and we know how to introduce things like carbon-carbon bonds now, where the R group is going to attack. It doesn't matter which one here because it's symmetrical, but this is under basic conditions. This does not have any acid around until later, and the nucleophile then is going to attack one of those carbons to become neutral, and then the oxygen gets a negative charge, and that's great. So in this type of system, you are now able to make carbon-carbon bonds as efficiently as we did with carbonyls. This sort of parallels the carbonyls and gives you more flexibility. To start this out, to go back even further, thinking about going back all the way to carbon or to an alkane. You start out with an alkyl bromide. What's a very simple, appropriate precursor to a bromide? An alcohol, right? An alcohol can be turned into a bromide can be turned into a grignard can then attack an epoxide, or it can attack a carbonyl, and all of a sudden you're doing real organic synthesis. And that last step there, typically the book is showing water as the acid, it doesn't matter. That gives the proton here, and we end up with a product. So we now have some very powerful chemistry to be able to make organic systems, to be able to expand things. Dominic? The solvent, that's exactly right, the solvent. You don't worry about it, it's not involved in the chemistry, it does not participate. Yeah, it's just there to solubilize everything and make sure everything works. So there's the sort of take home from that idea there, where the 2 carbon piece can now be brought in if you use an epoxide. And so your group that you brought in is 2 carbons away from the OH group. It's on the adjacent. As opposed to when you do carbonyl chemistry, it goes on the same carbon. Now this slide, if you're not sure what I'm talking about here, make sure you see this slide. With the epoxides, you ended up with a system in which the R group is on the adjacent carbon to the hydroxyl. Previously, in the earlier chapter, when we did the organometallic chemistry and you made this into RMGBr, and we know that this goes after the aldehyde and adds, the R group ends up on the same carbon as the OH group. That makes a difference now, and that will be important in your planning. So you'll have to get to some point, maybe in some of these problems, where you say, okay, do I need an epoxide or do I need an aldehyde? And you know how to make both. You can take a primary alcohol and oxidize it to an aldehyde using PCC. You can take an alkene, which you can make from an alcohol or a bromide, and then turn that alkene into an epoxide, and then you can change the chemistry. So it is tricky stuff, but once you get it, it's kind of fun. Now, the very last thing in this chapter is trying to emphasize now that you are somewhat equipped to do these things in different ways. So there's not always the same exact synthesis. What I would say at this point is maybe be careful. If your synthesis is 24 steps long on next week's exam, there might be a problem there. Okay, because the synthesis that I put together is not supposed to be 24 steps. Your 24 steps might work, but while you're still on step 20, the rest of us are off doing something else. Okay, because we may be up to 5-step synthesis. And that's part of the game here, is to learn how to do that. So what we've got here from the textbook is a couple of problems in which you have to build off from this and turn it into that ketone or turn it into that ketone. Now, both involve carbon-carbon bond forming chemistry. It's obvious that at some point this bond has to get formed. And the most useful carbon-carbon bond forming reaction that you have seen so far this term has been the Grignard. So this must involve Grignard chemistry because it involves CC bond forming reactions. Don't worry about alkynes here because the starting material isn't an alkyne and it couldn't really be an alkyne. So in this case, it's Grignard chemistry. And we have to worry about making this thing either a nucleophile or an electrophile. How do you make carbon negative? Introduce a metal next to it. Introduce a metal next to it. So I probably want to make this thing into a Grignard at some point to make that carbon there delta negative. And then how do you make a carbon positive? We've seen that primary carbons can't be full positive, but they certainly can be delta positive, for example, by introducing things like bromides. This carbon now is delta positive because the leaving group is more electronegative. And so we have some compatibilities maybe. We can also make carbon positive by making it into an aldehyde, because that carbonyl carbon is very positive and will react with nucleophiles. And we can also make carbon positive by making epoxides. Those are our typical E+, if you like, electrophilic reagents that you will need to worry about to put some of these problems together. So the difference here in where the ketone is going to be kind of a regiochemical issue, isn't it? Or a different sort of structural issue. In this example, the carbon-carbon bond was made on the adjacent carbon to the one with the functional group. That tells you that it's epoxide chemistry. On the other side, the carbon-carbon bond is made on the same carbon as the functional group. That tells you it's carbonyl chemistry. All right? And you'd have a hard time switching them around. So to think about how to put this together, let's do this one first. What you would do is turn this into a Grignard by using magnesium. And then this is introduced to the epoxide. Now you would have a choice of doing acid or base chemistry here. With a Grignard, you've only got one choice. You can't use acid or else it'll kill the reagent. So we're doing basic chemistry here, and we're bringing in this species. Maybe this was made from propene. You epoxidized propene or something like that. You can make propene from propanol. Why is it attacking carbon 1 and not carbon 2? Steric environment. It's less crowded at carbon 1. It's a nucleophilic attack, so we're going for that particular carbon. And that gives us O- here. We've got our bond in the right place, but that isn't what we're after. When we quench this thing, we get an alcohol. The product is a ketone. What do you have to do to the alcohol to make it into a ketone? Oxidize. So what can I use down here? Give me some reagents that will work. Sodium dichromate with sulfuric acid, because you don't have to worry about overoxidation because secondary alcohols stop at the ketone. Anything else you can use? PCC or PDC, whatever you've got available. And that gives you that carbonyl in very high yield. So this was really now, I think, where we need to be and where we will go for the rest of the term, is this mixing up of carbon-carbon bond strategies with functional group manipulations to get to useful materials. And as we bring more functional groups in, it's quite an enjoyable sort of game that we play. That's okay. And that initial decision was made by the fact that the carbon-carbon bond I need to make is not directly attached to the carbonyl, it's next door. Now the other one, this was the opposite. In this case, the carbon-carbon bond, and this is what we do as chemists, you just sit there with a piece of paper and you scribble and hopefully come up with some ideas and things will fall into place if you understand what's going on. I need to make that bond right there. Am I going to need to oxidize or reduce eventually? I'm going to have to oxidize. Make sure you understand this. You don't know any chemistry that will directly form that bond. Right? You have seen that formation of that material in an ester reaction with a Grignard. Esters react with Grignards to give ketones, but what happens to the ketone after that? Esters react with a Grignard through nucleophilic acyl substitution, they form a ketone, but what happens to the ketone? It goes further. It goes into an alcohol, right? You cannot stop that reaction. It goes further. That tells you that if you try to do Grignard chemistry to make this, it isn't going to work because it's going to go further. You've already seen that within a different mechanism. So this bond now is going to have to be thought about in terms of an alcohol. You know how to make alcohols. And I'll mention this. Right? This is what we're doing in recitation. If we're doing this, the precursor to this, if you're doing a retrosynthesis, thinking backwards, has to be this species. Because alcohols are central to pretty much everything we've been doing so far. If you can get back to that species, you now have a method to make that bond. If you think about how to do this, we're going backwards. I'm breaking it into two pieces, one of which is starting to look like my starter material, and another piece that is going to look eventually like the other starter material. Now the question we have, and the thing that you have to sort of keep with you all the time, which piece do you want positive and which piece do you want negative? All the chemistry we've done has been knitting together positives and negatives. So this carbon here on this alcohol-looking thing, does that need to be positive or negative? Positive, right? Positive because it looks like an aldehyde. If you put a plus charge next to the oxygen, you can stabilize it with the lone pairs. And in reality, if I use this equivalent symbol, that's an aldehyde. And we all know how to make aldehydes. Now that says, okay, that's fine. That's your delta positive piece. That's the electrophile. We need to make this negative. You make a carbon negative by turning it into a Grignard. Clip the two things together, you get the alkoxide of this species, and then quench and oxidize and we're done. And that's where this comes in. So there's the aldehyde. That little process there of thinking backwards helps you work out that you need an aldehyde, not a ketone or an epoxide. Once you do this, you get the anion, you quench, that gives you the secondary alcohol, and then finally you can oxidize with any of these reagents, and that gives you the ketone. Now, none of that is particularly easy. It's absolutely impossible if you don't know the reagents. So over this weekend, something has to come together so that you can actually understand these things. Anybody got any questions? I'm pretty much done with 14. I think that's the last slide. Boom. I'll go back. Anybody got anything to say? What we have done to this point this semester is we have expanded from last term our toolbox. And I've used that phrase a bunch of times. The idea that organic chemistry, you know, we're engineers to an extent, and we've got to build things. We've got to understand some principles of strain and accessibility and what can work and what can't work. And that's one of our jobs. It's a big job. You know, if you get a chemistry degree, you'll get a job because we're you know, in demand. What we need to worry about now is the other part of what a chemist does, which is analyze. And it's always interesting, as you know, for me, being in this job for about 18 years now, very few people ever question what we say. Okay? And that's, no, that's something that to me is a bit of a concern, because you're assuming I know what I'm talking about. I do. Despite what Dr. Cooper says, I do. And your job as a scientist or an engineer or a pharmacist or a physician or wherever it is you want to be is to start to question things so that you make sure that you're getting the right answers. You make sure that you're happy with the data and people are telling you the truth. So as a scientist, what I need is a whole bunch of devices and a whole bunch of techniques to be able to work out what I've made. Because chemistry would be impossible if we just started throwing things together and got something out and we assume it's what we think it is. And that can be a big problem. And in fact, in my lab, half the stuff we've done in the past 5 years has been completely by accident because we didn't get what we expected. If we got what we expected, it would have been boring. We got more interesting stuff, and we find that out by doing something called spectroscopy. Now, chapter 15 and chapter 16, I'm only going to get through 15 for the test, and 16 is brilliant. Love it. I'm going to use these two words. I have this word here, I have this word spectroscopy, and I have this word spectrometry. Okay? And what's going to happen here, spectroscopy is, to me, a fundamentally different process to spectrometry. They're both ways of measuring things. They're both ways of looking at an organic compound with a technique and a device, usually an instrument, and actually coming up with an answer and a piece of information that helps me work out, I have an alkene, I have an alcohol, I have a benzene ring. Okay? To me, spectroscopy has always been about using light and using energy in a non-destructive sense. Okay? In a non-destructive sense. In other words, you put a sample in the presence of some energy source, and the sample does something. It vibrates, it absorbs, something like that. But you get it back at the end, right? The molecule relaxes, the energy is spent, and then you get the molecule back, and the sample is the same as it was. The difference with mass spectrometry is that you blast the molecule apart, right? You destroy it, and you're not getting it back. So that's my understanding of what the difference is with the two words. Now, the two techniques we'll do here in chapter 15 are very, very useful. IR, you could spend a whole year talking about IR spectroscopy. You know, there are books on this subject, and it's a huge subject. Likewise with mass spectrometry. We have a couple of days to do it, right? In fact, we have a couple of hours to do it. But what I'm going to try and do here is give you an understanding of what we do and why we do it, so that as you head towards exams and even in the future, maybe some research, you know when to do what. You know that I'm looking for a certain answer. What instrument will I need to use? All right? We're not usually doing this blind. We're not usually doing 15 tests and then picking out the best one. We're picking the instrument to use. So what you will get over the next few days, I hope, is a working knowledge of these techniques. Now, that sheet that's in front of you, okay? That sheet is your best friend. These techniques are reliable. You will see in an infrared spectrum, if it's an alcohol in the molecule, it will always have a big signal at 3200 in what we call wave numbers. It's always there. In NMR spectroscopy, when we get there after the exam, if you see a signal at 7, it's probably a benzene ring, because that's where they always show. So this is reliable. Now, I want to point out one word on that sheet. It's at the top. It's approximate, right? It's approximate. And by approximate, we mean 0.1, 0.2 here or there, right? If you see a signal at 7, it probably isn't a simple alkyl group. If you see a signal at 0 in the NMR spectrum later on, it probably isn't a benzene ring. They're way out. But within reason, those numbers are the understood values for those types of functionalities or those types of atom in that particular technique. So chapter 15 sets this up by thinking about what type of energy we can use to hit an organic molecule with and then see a response. Now, if you like analysis, this is great. This is a puzzle. The second exam is always fun because we've got the NMR spectroscopy done by then, and we can do it. We can put it all together. You know, we can give you a synthesis, and you've got to decide how to analyze it on paper, and it's actually quite enjoyable. So, without any physics, I mean, this picture here is just there to show you. You know, it's a nice picture, but we're not concerned about the physics here. What we are concerned about is the different types of incident radiation that we can use to give an organic molecule energy. Light. We can think about infrared, we can think about visible, different types of the spectrum, we can think about microwaves. In terms of organic chemistry, if you've seen this before, which I hope you have at some point, we're interested in the far right side, microwaves. We can use microwaves in synthesis, not so much in this class. Infrared, definitely. IR is very useful. You'll be doing it in lab this week. Near infrared, you don't see so much of that here, but you can use it in spectroscopy. Visible, I mean, we are doing spectroscopy, okay? The fact that Kyle's shirt is some, I don't know, Oregon duck color, horrible, nasty green, whatever it is, My eyes are doing visible spectroscopy because I can see that color, right? Your horrible Oregon Duck shirt is absorbing in that particular part of the spectrum. It's what? It's not Oregon. That's okay, I forgive you. We'll see that when we get to the next chapter when we do ultraviolet visible spectroscopy, and we see that conjugation, double bonds next to each other, make a difference in terms of color. Now, in terms of ultraviolet, to the left up there, we'll spend some time on that. That is not a very useful technique for organic chemists. It is very good for biochemists to look at proteins and look at DNA and stuff like that. We do not do that much. What we will spend a lot of time on is we'll talk about infrared, and we'll talk about, later on, we'll talk about magnetic environments, and we'll talk about radio waves. At the left, cosmic and gamma rays, no. We're not using those in spectroscopy. Okay? X-rays, absolutely, but we don't talk too much about it here. If you're interested in X-ray spectroscopy, YSU has probably the best collection of X-ray diffractometers, probably in the Midwest at the moment. Okay, it's very impressive, and you can take classes to actually learn how to use those things. So I'm going to start off today talking about infrared, and then talking about what that sheet is there for. This can be confusing if you let it be confusing. It can be a lot of fun if you spend time on it and get into it. It is how it's the how do we know what we get type of idea. So here's the list of what we'll talk about over the next 2 or 3 weeks. Before the exam, it will just be IR and mass spec, but it will be useful. Infrared spectroscopy is the response of bonds within organic molecules to infrared light. They vibrate. You put light in, you energize the molecule, it changes the vibrations, you make them vibrate faster, and you can measure that. And certain bonds will have certain vibrations that others won't. So you can differentiate between, let's say, a hydroxyl and a carbonyl. And you will see in lab this next week that if your molecule contains a carbonyl, the list of unknowns that you're given, you'll be able to work out which one it is. NMR spectroscopy, which is chapter 16. This is the response of magnetic nuclei. Magnetic nuclei, fortunately for us, protons, carbon-13, which are in all our molecules, phosphorus, and fluorine, things like that. All molecules, or all atoms, I should say, that are important in medicinal chemistry. We have techniques to be able to see those things. And you have to put this thing in the presence of an external magnetic field and hit it with a radio frequency. And if you're interested in this, I'll show you our lab over in Ward Beecher, and we have a very, very nice setup there for NMR spectroscopy. That's the most important one to me. UV vis, a little bit we'll talk about. The basics of it, how it works, and what information you can get. And then mass spectrometry is the second half of chapter 14, and that is something that, again, we can do in Ward Beecher, and this tells you obviously about mass, tells you about size of fragments. Well, all of this is based on a very simple idea, right? So if Pierce is sitting down, Pierce is relaxed, right? If Pierce stands up, stand up, Pierce. You knew I'd do this, right? And stand up for the rest of the lecture, okay? You'll be pretty annoyed because you'll be tired, yeah? And it takes energy to stand up. You can sit down. It takes energy to stand up. So we've got PS1 sitting down and PS2 standing up. Or we can talk about that in general, saying about E1 and E2. Low energy, high energy. So without any too much physics, you can promote systems from low energy to high energy by putting energy in. Yeah? You can promote, and you can make them go from one to the other. On the right-hand side, maybe it's a bit more complicated, in which it's not simply E1 and E2. You have a bunch of different states that you can go between. And if you're interested in that, maybe physical chemistry in the future, engineers, PChem, you'll love it. Those ideas are important. But all we're going to do here is put energy in and see this change from one to the other. And all of this stuff up here is just to make you understand that there are relationships between wavelength and energy, between frequency and energy and stuff like that. And don't worry about memorizing any of that stuff. Just that each of these techniques is a different type of energy from that spectrum that will then allow an organic molecule to do something different, and we can measure what's happening. So an infrared spectrometer is another box that you put a sample in. Be very careful this week when you do this. It's an expensive piece of equipment. You open up that little grey hatch there, and you put a sample inside. And word of warning, who's done this lab so far? Has anybody done this lab yet? You're about to. Okay, you're about to start this, what, Tuesday next week? Yeah. Now, the sample you put together is a sandwich. You take 2 cylinders, 2 discs of sodium chloride. And sodium chloride does not show up in the infrared spectrum, so it's blank. And you're going to use these as a mount to put your sample on. You take a drop of your liquid, put it in between these 2 little glass plates, put them together, and you get a film. And that film is your sample. And the infrared light, which is generated in this box, will go through that sample, and if there's an organic molecule in there, it'll absorb. And depending upon what's in that molecule, you'll absorb in different places. And then you get a readout based on what happened in the box, and you see a spectrum. Now be very careful. These things are made of salt, sodium chloride. They're very expensive. What do you not wash them with if they're made of salt? Thank you, water, right? Don't wash them with water. If you do, Dr. Jackson will get very upset, right? Do not wash them with water because they'll dissolve. Wash them with acetone, and you'll learn how to do that next week. But this is a very powerful technique because you can see all sorts of things happening, and you can generate what's called a spectrum. Now, let's get the language right. Spectrum is singular. Spectra is plural. So this is an infrared spectrum. First of one of these charts, these graphs, these spectra that you have seen. And I'm not going to go into as much depth as the book. I'm not going to give you all the physics and all the stuff here. I'll present it, but I'm not going to test you on it. I want a working knowledge of how you can use these signals, these absorbances, to work out a problem, to work out what an unknown molecule is. That's what we use it for the most. So in this case, we're talking about the types of bonds in molecules. And you can see here an OH group, and you can see a whole bunch of CC and a whole bunch of CH bonds. That spectrum, when you see it, you'll see by Monday, if you get on this at the weekend. All day, that's an alcohol. That signal there, around 31, 32, 3250 on our scale, is an alcohol every time. Okay? And then there's not much going on here. It's kind of blank. This is all about CH bonds, and this is all about CC bonds. So these graphs, which you're given, are going to be useful for determining structure. Now think about this. Do you memorize those numbers on your chart? No, because that chart is the last page of your exam. And the first thing you start doing on Friday is you take off that last page, and you can use that to solve the problems. And you can take it home, put it on the fridge, whatever you want to do. It's yours. But it will be on there, because Dr. Jackson and I very early on decided that rather than have you memorize all this stuff, okay, you have that with you, you can use it. It's a guide to help you solve problems. So what's infrared about? It's all about bonds bending and stretching, and it's all about absorbing energy and making the molecule go a little bit crazy. And we can see here some modes of this vibration. If you want to learn more about this, we can probably teach you a class at the senior level in which you talk about every single line in those spectra. But at this level, we're interested in only maybe about 10 lines at most that give us information. So I hope this works. Look at that. Look at that. That's what's happening. Okay? On the left, you've got this rocking motion. That's an absorption that you can see. In the middle, a wagging, right? Sort of cheerleader type thing. Then you've got the twisting. And molecules do this anyway, but you can make it go faster if you put energy in. And you're measuring each of those types of absorbances. That's all there is to it. I'll do it again. I know. You like that, Sammy? Yeah, just take a nap. Okay. Those numbers are on that chart. And we have condensed those numbers from the vast array of numbers that you can get from these signals to the ones that are important to the context of the class. At the top left, I've got the word approximate again. Absorption frequencies, centimeters to the -1. So we use what are called wave numbers, and it's related to frequency. So that bottom axis on my scale, I'm going to start showing you these types of graphs very quickly in a second. That bottom axis down there, wave number, is related to frequency. And then this, transmittance, is basically how much light gets through. Or you could call it absorbance and how much light gets absorbed. So you have an X and a Y. You're only really interested in the X-axis. Those numbers are where we're going to go. So the background to this, oh, there you go. We can develop pretty quickly an idea that strong bonds have a certain frequency, weak bonds have a certain frequency, triple bonds, double bonds have different frequencies, and then we can start to use this chart. And what I need to do probably today before the weekend is point out that these are ranges. You can imagine that the vast differences that you've seen in organic structures. Even a tertiary alcohol going from one tertiary alcohol to the next might have a different structure. One's maybe on a cyclohexane, one's on an acyclic molecule. They're quite different. They will bring in some constraints in terms of how things vibrate. So you're not going to see exactly the same answer every time. You're going to see within a range. So these ranges become fairly obvious. If you have a if you have an alcohol OH group, that's a dead giveaway. I'll show you one in a second. If you have a carboxylic acid, it's in a similar range, but maybe it's shifted a little bit. We can talk about amines. They're in a similar range. And all of these differences here, this will be important. You can tell whether you have an alkene by the fact that you have a stretch in a certain place for an sp2 carbon bonded to an H. or an alkyne, an sp carbon bonded to an H. You can get that specific about it. And those numbers are on there to help you. Double bonds are very important. We'll talk about carbonyls, obviously, and alkenes, which we've made. And you can see where this is going. The context of this is now use it as a technique to work out what you did. And I've set problems, I will set problems in which I bring up some experiment that we've just invented, and here's the data. Here's what we started with, here's the chemistry, and here's the data. What happened? Your job is to work backwards with the data in front of you and prove what happened in the experiment without having the answer in front of you. We can see different numbers for alkenes. We do spend a lot of time on the right-hand side of the spectrum. Okay? We will see that these numbers now become very useful for working out on a benzene ring how many substituents you have and where are they. Benzene chemistry comes up, I think, after spring break, roughly around there. But those numbers now, whether there's one number or two numbers, whether it's a 700 number or a 600 number, will make a difference in terms of whether you think it's a benzene ring which is symmetrical or not symmetrical. A bit more about that later, but that's why that's there. Okay, there's the sort of physics behind it. Don't worry about that equation. If you take analytical chemistry in the future, maybe you'll see that again. But the overall understanding is that bonds will show at different parts of that spectrum depending upon what's attached. And you think of this as a spring. Short spring or a long spring, right? You're going to get different vibrations, different frequencies. And here you can see that the left-hand side of the spectrum is typically for carbon-hydrogen bonds. Now, what is D? It's deuterium. How is deuterium related to H? It's H2, isn't it? It's H with an extra neutron. So remember that. We'll use that a lot in the NMR spectroscopy. But there is a difference, you see, between C and H. This one is at 3,000, this one is at 2,200. H is atomic mass 1, D is atomic mass 2. You've got a bigger sphere at the end of this spring. It's going to change its frequency. CO heading to the right, CCl heading to the right again. You do get quite a dramatic difference in terms of those absorbances. The vast majority of the time, you'll be worried about this one and this one, because that's what we've been dealing with up to this point in terms of the chemistry. So don't worry about the equation right there. Just recognize that this is, it's all about two little spheres on a spring, and they're vibrating, and depending upon what those spheres are, you get different frequencies. Now, what we should worry about is where these things show up in graphs. Where do they manifest in the charts? Well, triple bonds to the left, they're stronger, they'll have higher frequencies. That would be the left of the spectrum. C double bond N in the middle of the spectrum. This is going to be a very, very important region for you to work out whether you have an aldehyde or a ketone or a carboxylic acid or an alcohol or an alkene. To the right, Cn, this tends to get buried. You will see some of the graphs that I show you starting today, that this region down around 1100 down to 800 can be very dense. It can be quite difficult to pick out numbers from there. But there'll always be enough information to solve the problem from someplace else. So this at the bottom is sort of a rough look at the general places on the spectrum that you have to worry about. To the left, greater than 2700, typically around 2800, 3000, 3300, you're going to see XH bonds. That could be CH, it could be OH, it could be NH. In the middle, you get a region that we use a lot in my lab. We might not use so much here, but triple bonds. C triple bond N, C triple bond C show up around 2100. And that's nice because it's unique and it's set apart from all the others. Carbonyls, C double bond O, C double bond C, you're in this region 1850 down to 1600. And the strength of these signals will be a dead giveaway. If you see a carbonyl, it's a very strong absorbance, and it's always a dead giveaway. If you see an OH, it's always a strong absorbance. Gets a bit more tricky over here because this is going to be called the fingerprint region, where there's a lot of stuff going on. It might be more difficult to pick those things out, but you do have enough information along the way. So I'm going to finish this off in a couple of minutes, and then I'm going to do it again on Monday. This never sinks in the first time. Do it again on Monday in the context of thinking about problems. In this example, we just said that stronger bonds have higher frequencies. This is then again manifested by carbon-hydrogen single, carbon-hydrogen double, carbon-hydrogen with a triple bond next to it. Because the hybridization is changing from sp3 to sp2 to sp, and the bonds are getting a bit stronger as you go. Now, in terms of the background to that, there's the p orbital, and then sp3, sp2, sp, more electronegative, and those bonds will have different vibrations based on the fact that they're shorter or longer. What we need to worry about is looking at graphs, looking at charts. So get chapter 14 out the way as soon as you can. That quiz will go online today, and it'll be due next Thursday. Get that done as soon as you can so you can get into this stuff. In the textbook, we have these pictures, which are showing you how detailed this can get. in terms of the use of simple absorbances to differentiate between quite different compounds. On the left, the CH bonds, all of those vibrate in this region, between 2800 and 3000. There's nothing over here. Okay, there's nothing to the left of that line. Whereas if you go to a CH bond and an alkene, which has a different frequency because it's a tighter bond, you get a shift. And that shift now is over there, and that looks to me like around 3100 maybe, 3050, something like that. And what you'll find yourself doing, I hope, over the weekend with that sheet in front of you, is going backwards and forwards. And your job, I think, is to pick that up. How do I use that chart? It's no use to you whatsoever if you don't know what those numbers mean. That's the first thing you learn. And then finally, on this slide, you're looking at CH bond and an alkyne. It's moved to the left again. That's a giveaway. That's a giveaway there. It's a sharp bond, a sharp signal, and it's around 3250. That tells you have an alkyne in the molecule. So what I'm trying to exemplify here is that very quickly, by Monday, you should be able to look at one of these graphs and be able to get into the problem and decide what is it. Is it an alkane? Is it an alkene? Is it a carboxylic acid? Stuff like that. So here's my last slide for the day. And then you've got time to think about this over the weekend. We'll do this again Monday. Here is a typical example of an infrared spectrum. And that is, I think it's hexane. No functional groups, but it still has an IR spectrum, right? IR spectroscopy is all about functional groups. This does not have a functional group that we are familiar with, but CH bonds still will do this and CC bonds will still do this. And you can see that this is a fairly complicated spectrum. There's nothing here. No OH group, no alkyne. And then you get all this stuff, which is CH. Why do you think it's so busy? Why do you think you get so many signals? You have lots of different types of CH bonds. They're not all the same, right? Some are primary, some are secondary, some are buried in the molecule, some are towards the end. They'll all have slightly different frequencies. And then you go to the right-hand side, and very quickly, over the next few days, you'll recognize, all right, 1600, 1700, there's nothing. It means no carbonyl. It's not there, it's not a carbonyl. And then you get over to here, and you start to see some of these carbon-carbon bonds, and again, because there are so many of them, primary to secondary, secondary to secondary, you're going to see all those different vibrations in what we call the fingerprint region. That tends to get a bit busy. Last thing I'll say today, this stuff is very, very useful if you get onto it. It'll help you with problems next week. It'll help you solve problems in the future as we build up with all the different spectroscopies to the point where you have 5 pieces of data in front of you and you have to be coming up with a problem, coming up with a structure. So have a good weekend. See you on Monday.